Okay, so I'll start going over the solution to this checkpoint. So the first term of the sequence is 11, just because it's the first in the list. So this is the value of A1, which is 11. And then the common difference, we can find the difference between consecutive terms. So all of these are 6. And it's expected that all of these differences will be the same just by the definition of an arithmetic sequence. So we denote this common difference by 6. So now we want to find the sum of the first 10 terms in this sequence. So if you recall from the previous slide, now this is a1 plus an over 2 times n. So our n is the number of terms we are summing, which is 10, given by this question. And you have a1 is 11, and an, so this is the last term that we will be summing. This is going to be a10, which is a1 plus 10 minus 1 times d. So you have a1 is 11, and we have d is 6. So this is 11 plus 54, which is 67, or 65, sorry. So then we have, this is equal to 11 plus 65 over 2 times 10. So 65 plus 11 would be 76. And then we have times 10 over 2, which is 5. This is equal to 350 plus 30, which is 380. So that gives us the sum of the first 10 terms of this arithmetic sequence. So now we have this example. How many terms are in the arithmetic sequence 8, 11, 14, so on until 35? So for these types of problems, so first we know that the number of numbers in this sequence is simply n, just because it's the first 10 numbers. So to count the number of terms in this arithmetic sequence, we want to transform the sequence into something that looks like 1, 2, all the way up to some number. So to do this, we notice that we want to get consecutive numbers, and since our common difference is 3, dividing by 3 would give us numbers that differ by 1. But that gives us fractions, so we want to subtract 2 from each term in the sequence. So if you subtract 2 from each term in the sequence, we get 6, 9, 12, all the way up to 33. And now we can divide each term in this sequence by 3. This gives us 2, 3, 4, all the way up to 11. And then if we subtract 1 from each term in the sequence, we get 1, 2, 3, all the way up to 10. And in this sequence, there are 10 integers. So basically, in each step, we're changing each term of the sequence, but this does not affect the length of the sequence. So that's why we can do those steps. So now we have this example. Given an arithmetic sequence with first term a1 and common difference d, find a formula for the sum am plus 1 all the way up to ak. So to do this, we have so basically this sequence am plus 1 all the way up to ak is also an arithmetic sequence because a is an arithmetic sequence. These are also going to differ by d, but instead of first term a1, we have first term am. So let's just define a new sequence b. So the first term of b will be am. The first term, or the second term of b will be am plus 1. Then we have bk minus m plus 1. So this is basically these terms am plus 1 all the way to ak. So we want to find the sum. So now our sum becomes b1 plus b2 all the way up to, And we know that this is k minus m plus 1 because the number of terms in the sequence, m plus 1, all the way up to k, we can subtract m minus 1 from each term. So you get 1, 2, 3, all the way up to k minus m minus 1. And this sequence simply has k minus m minus 1 terms, which is k minus m plus 1. So to find the sum of these terms, again, we have the number of terms, which is k minus m plus 1, times b1 plus bk 1 over 2. And this is from the formula we had for Sn, which was n times a1 plus an over 2. And then we can put these values in for b1. So we have this is equal to k minus m plus 1 times a1 plus, or am plus ak over 2. So again, we have the average of the first and the last terms of our sequence, am and ak, and then we multiply that by the number of terms in that sequence. So now we have this next example. So in the 5-sided star shown, the letters A, B, C, and D are replaced by the numbers 3, 5, 6, 7, and 9, although not necessarily in this order. The sums of the numbers at the ends of the line segments AB, BC, CD, DE, and EA form an arithmetic sequence, although not necessarily in that order. What is the middle term of the arithmetic sequence? So first, let's find the sum of the arithmetic sequence. Since each vertex lies on exactly 2 sides of the star, the sum of the arithmetic sequence, they have 2 times 3 plus 5 plus 6 plus 7 plus 9, and this is 60. So since the middle term of an arithmetic sequence is just the average of all the terms, our answer is simply 60 over 5, which is 12. So our next example is in an arithmetic progression, the ratio of the sum of the first r terms to the sum of the first s term is r squared over s squared, where r is not equal to s. Find the ratio of the 8th term to the 23rd term. So using our formula, Sn is equal to, we have 2 forms for Sn, if you recall. We also had this as n times a1 plus n minus 1 times n times d over 2. So for this problem, we'll be using this form. So we have the sum of the first r terms is SR, which is r times a1 plus r times r minus 1 d over 2. And similarly, we have the sum of the first s terms is s times a1 plus s times s minus 1 and 2. So we're given that the ratio of the first r terms to the ratio of the sum of the s terms is r squared over s squared. So this gives us that our SR over s times a1 plus s times s minus 1 times d over 2. So we're given that this is r squared over s squared. So let's cancel a common factor of r in both of these numerators and a common factor of s in both of the denominators. So we're left with a1 plus r minus 1 times d over 2 over a1 plus s minus 1 times d over 2 is equal to r over s. So the problem wants us to find the ratio of the 8th term to the 23rd term. So by the definition of the arithmetic sequence, we have the 8th term is a1 plus 8 minus 1, which is 7, so 7d, and a23 is equal to a1 plus 22d. So we want to find this quantity, a1 plus 7d over a1 plus 22d. So basically we want r minus 1 over 2 to be 7, and s minus 1 over 2 to be 22. So that gives us the correct numerator and denominator. So if r minus 1 over 2 is 7, then we have r is equal to 15. And if s minus 1 over 2 is 22, we have s is equal to 45. So we have this is equal to 15 over 45 if we were to plug these values in. And this can be simplified to 1/3. So now we have this checkpoint. Let A be any arithmetic sequence. Given that am plus 1 all the way up to plus an is equal to sp minus sq, find p and q in terms of m and n. And we're using the definition of sk we have been using. Sk is the sum of the first k terms. And you guys can try this yourself. Okay, I'll start going over the answers to this checkpoint. So basically we want to write this in terms of s something minus another s term. And so basically we see that this indices of this term to go up to n. So we can try to start with Sn. So this gives us a1 plus a2 all the way up to plus am minus 1 plus am plus 1 all the way up to an. And now we see if we can get rid of these terms right here, we will get our desired sum. But this is simply Sm minus 1 because this last term is am minus 1. So hence we have this sum am plus 1 all the way up to an. This is equal to Sn minus S minus 1. So our P would be n and our Q would be m minus 1. So now we'll move on to geometric sequences. So the definition of a geometric sequence is that it's a sequence of real numbers in which the ratio between any term and the term before it is constant. This ratio is known as the common ratio, which we denote by r. So an example of a geometric sequence would be 3 is our first term, and 6, 12, 24, 48, 96. Because 6 divided by 3 gives us 2, 12 divided by 6 gives us 2, 24 divided by 12 gives us 2, and so on. So this is our first term of the sequence, a1, and we denote this common ratio by r. So we have r is equal to 2 and a1 is equal to 3 for this geometric sequence. So using the definition above, it follows that the nth term of a geometric sequence is given by this equation. An is equal to a1 times r to the n minus 1. So basically, to find the nth term of the geometric sequence, we take the first term and multiply that by the common ratio raised to the n minus 1 power. So for example, in the previous example, we had 3, 6, 12. So to find the fifth term of the sequence, we would take our first term 3 and multiply that by the common ratio 2 to the 5 minus 1. So this is 4. So this is 3 times 2 to the 4. Should be 48. So we have this example. A tree doubled its height every year until it reached a height of 32 feet at the end of 6 years. What was the height of the tree at the end of 3 years? So basically, if we take the height of the tree every year, we'll get a geometric sequence because the term is doubling every year. So if we have 32 as our sixth term, in the previous year, we have to half that to get the height in the fifth year, which would be 16. So basically, if we have A6, our sixth term is 32, and our R is 2, we want to find A3, which is the height at the end of 3 years. So basically, we have that A3 times R to the 6 minus 3. This should give us A6. And we get the 6 minus 3 from this 6 and this 6. And we know that R is 2. So we get A3 times 2 cubed, which is 8. This should be A6. And we're given that this is 32. So hence we have A3, which is the height of the tree at the end of 3 years, is 32 divided by 8, which is 4 feet. Now you guys can try this checkpoint. What is the fifth term of a geometric series that has a first term of 16 and a common ratio of 3/2? Okay, so for this problem, we can simply use the formula for the nth term of a geometric sequence, which is a1 times our common ratio to the n minus 1 power. So we are given that a1, the first term, is 16, and r is 3/2. And we have that a5, which is the fifth term, is equal to a1, which is 16, times 3/2 to the n minus 1, and n is 5, so this is 4. So this is equal to 16 times 3 to the 4, which is 81, divided by 2 to the 4, which is 16. This gives us 81. So now we have this theorem for geometric sequences. So if the sequence A, geometric sequence A, has length n, then the sum of the terms of A is a1 times 1 minus r to the n over 1 minus r, where r is a common ratio. And then if A has infinitely many terms and our common ratio has absolute value less than 1, then the sum of the terms of A is the first term divided by 1 minus r. And if A has infinitely many terms and r is greater than or equal to 1, then the sum of the terms of A is plus or minus infinity. And given the sign of the first term, so if a1 is positive, then our sum is infinity. And if a1 is negative, then our sum would be negative infinity. So these two formulas are pretty important. And so to see this, we want to find the sum. So for this formula, we want to find the sum a1 plus a1 times r plus a1 times r squared, which is just a1 plus a2 plus a3. So we're just summing the terms. So let's call this sum s. And we have r times s equal to r times a1 plus r squared times a1 plus r cubed times a1, so on. So if we were to take s minus rs, we see that this a1r cancels with this a1r squared cancels with this a1r squared, and so on. So we're just left with this a1 term. So this is s times 1 minus r equal to a1. So we get that s is equal to a1 over 1 minus r. And to find this, to derive this formula, you do the same thing and multiply s by r and then take the difference, s minus rs. So now we have this example. An infinite geometric series has sum 2005. A new series obtained by squaring each term of the original series has 10 times the sum of the original series. Find the common ratio of the original series. So let our original geometric series have first term a1 and common ratio r. So we're given that the sum, it has sum 2005. And from the previous slide, you can recall that the sum of an infinite geometric series with first term a1 and common ratio r is a1 over 1 minus r, and that this is 2005. So now our new series is obtained by squaring each term of the original series. So the terms of the original series are a1 times r, a1 times r squared, a1 times r cubed, so on. So if we were to square each term, we would get a1 squared r squared, a1 squared r to the 4, a1 squared r to the 6, so on. So the common ratio now is r squared, because we have r to the 4 over r squared is r squared, and so on. And then our first term is a1 squared. So the sum of this sequence is going to be the first term, which is a1 squared, over 1 minus the common ratio, which is r squared. So we're given that this is 2000. or 20,050 because it's 10 times the sum of the original series. So we can divide this by this. So you get 10 is equal to a1 squared over 1 minus r squared over a1 over 1 minus r. So this is equal to a1 squared over 1 minus r squared times 1 minus r over a1. So this is 1 plus r because 1 minus r squared is 1 minus r times 1 plus r by difference of squares. And this is a1. So we have a1 over 1 plus r is equal to 10. We have a1 over 1 minus r is 2005. So this becomes a system of linear equations. We have that a1 equal to 2005 minus 2005 times r by cross multiplying. We can do the same for this equation. Of a1 is equal to 10 plus 10r. So we have these two expressions in r are equal. At 2005 minus 2005 times r equal to 10 plus 10r. So this is, we can bring this over to this side to get 1995 is equal to 2015r.
Huh? I need a math class.
So we get r is equal to 1995 over 2015.
I need a math class.
And we can simplify by dividing both the numerator and the denominator by 5, which gives us 399 over 403, I believe. So this is the common ratio that we were looking for. So next we will be going over arithmetical geometric sequences. So the definition for this type of sequence is that it's a sequence in which each term is a product of a term from an arithmetic sequence and a term from a geometric sequence. So basically, our terms are a1 over b1, a2 over b2, a3 over b3. For a1 is an arithmetic, or a is an arithmetic sequence, and b is a geometric sequence. So for example, we could have 2 over 3, 4 over 9, 6 over 27, 8 over 81. So we have 3, 9, 27, 81 is a geometric sequence, and 2, 4, 6, 8 is an arithmetic sequence. So this would form an arithmetical geometric sequence. So our first example is to evaluate this sum. So these terms are the terms of an arithmetical geometric sequence because the numerators are 1, 2, 3, 4, which is an arithmetic sequence, and the denominators make up a geometric sequence with common ratio of 2. So let's denote this by S. This for S. And then, so in general, when finding sums, you usually multiply S by the common ratio of the geometric sequence. And in this case, this common ratio is 2 because 2 squared over 2 to the 1 is 2, 2 cubed over 2 squared is 2, so on. Then this is 1 plus 2 over 2 squared times 2. So that's 2 over 2 to the 1. And this next term times 2 is 3 over 2 squared. So basically, we're just decreasing the exponents of 2 by 1 in each of these terms, 4 over 2 cubed. So now we can take the difference of 2s minus s. So we have this one term, and then we can look at the difference between these terms. We have 2 over 2 to the 1 minus 1 over 2 to the 1. This is 2 minus 1 over 2 to the 1. And then for this difference, we have 3 minus 2 over 2 squared. We have 4 minus 3 over 2 cubed. And notice that all of these are just 1. So this is equal to 1 plus 1/2 plus 1 over 2 squared plus 1 over 2 cubed. And we know how to sum this because this is just a geometric sequence, infinite geometric series. So this is a geometric series with first term 1 and common ratio 1/2, because each term just getting multiplied by 1/2 for the next term. So this sum right here would be 1 over 1 minus 1/2, which is simply 2. So we have 2s minus s, which is just s. This is equal to 2. So this gives us our desired sum. So next we have this example. We want to evaluate this sum. So basically, this notation just means we start with k is equal to 1, and then add it for k is equal to 2, and then for k is equal to 3, so on. So for this example, so let's call this s. S is equal to just writing out the first couple terms, 1 squared over 3 plus 2 squared over 3 squared plus 3 squared over 3 cubed, 4 squared over 3 to the 4, so on. So again, we'll multiply s by the common ratio of the geometric sequence, which is 3. Get 3s is equal to 1 squared over 3 to the 0, which is just 1, plus 2 squared over 3 to the 1, because when we multiply this by 3, the exponent of 3 in the denominator gets reduced by 1. And we get 3 squared over 3 squared plus 4 squared over 3 cubed plus 5 squared over 3 to the 4. So now let's subtract 3 or s from 3s. We get this 1 squared, and then we'll subtract these terms with common denominator. We get 2 squared minus 1 squared over 3 to the 1. So 2 squared minus 1 squared would be 3. And then we have this 3 squared minus 2 squared, which is 5. And then 4 squared minus 3 squared, which is 7. And then 9 over 81. And notice that this part right here is an arithmetical geometric sequence because we have 3, 5, 7, 9, which has common difference 2, and the denominator are getting multiplied by 3. So the reason we get the sequence 3, 5, 7, 9 here is because basically we're taking k plus 1 squared minus k squared. So here we have 3 squared minus 2 squared, so like our k is 2, and here we have a 4 squared minus 3 squared, so our k is 3. So we can expand this, k squared plus 2k plus 1 minus k squared, and this is 2k plus 1. So this gives us a arithmetic sequence with starting term 1 and a common difference 2. So we have 2s is equal to this 1 plus this arithmetical geometric sequence. So now let's find the sum of that arithmetical geometric sequence. So we have this. So let's call this value r. Then we're going to multiply r by 3 because, again, the common ratio in the denominator is 3. We get 3 plus 5 thirds plus 7 ninths plus 9 over 27. So now let's take 3r minus r. So again, r is just this part. We're not looking at the 1. So we have this 3 term. And then we have 5 thirds minus 3 thirds, which is 2 thirds. And then 7 ninths minus 5 ninths is 2 ninths. And then 2.7, so on. And this is a geometric sequence with first term 2 thirds and common ratio 1 third. So this sum is just going to be 2/3 over 1 minus 1/3. And this is just 1. So you have 3r minus r is 4. So 2r is equal to 4. So r is equal to 2. And then we have from here, 2s is equal to 1 plus r. And this is 3. Hence we have our original sum is 3/2. So basically the main technique in this problem is just to multiply your sum by the common ratio of the geometric series in the denominator and then subtract those two expressions. So now you guys can try this checkpoint for yourself. Find the value of s given this expression. So this is an arithmetical geometric sequence, and this term should actually be 2k minus 1 over 3 to the k. Okay, I'll start to go over the solution now. So we have s is equal to 1/3 plus 3/9 plus 5 over 27, so on. So again, we'll multiply s by 3 because that's the common ratio in our denominator, because 9 over 3 is 3 and 27 over 9 is 3. So we get, this is 1 plus 3 over 3 plus 5 over 9 plus 7 over 27, so on. So now we look at the difference. We have this 1, and then we look at the difference between terms with common denominator. To get a 3 over 3 minus a 1 over 3 is a 2 over 3. Then a 5 over 9 minus 3 over 9 is a 2 over 9. And then we get a 2 over 27, so on. So this is it's a geometric sequence with first term 1 and common ratio, let's just look at this part, because this is not included in the geometric sequence. Have first term 2/3 and common ratio 1/3, because 2/3 times 1/3 gives us 2/9, and so on. So the sum of this part will be a1, which is 2/3, over 1 minus our r, which is 1/3, and this denominator just 2/3. This gives us a value of 1. So we get 3s minus s is equal to 1 plus 1. We get 2s is equal to 2. So we get s is equal to 1. And now we will go over telescopic sums and products. So this is a useful technique when it comes to finding a sum or a product. So telescoping is a useful technique to write each term in such a way that when you rewrite all the terms, almost all of them cancel out, except a couple of them. So telescoping can often simplify sums and products, especially ones that contain fractions, trigonometric functions, and factorials. So this problem is an example of telescoping. So we want to find the sum. So when we want to use telescoping, we usually want to write each term as a difference of terms. So for this problem, we use the identity 1 over k times k plus 1 is equal to 1 over k minus 1 over k plus 1. Because if you were to cross multiply, you would get k plus 1 minus k over k times k plus 1, which gives us 1 over k times k plus 1. So as you can see, we wrote all the terms in this sequence, which are of the form 1 over k times k plus 1, as a difference of terms. So now we can rewrite this expression as, so in our first term we have k is equal to 1, then we have k is equal to 2, all the way up to k is equal to n. So we have 1 over 1 minus 1 over 2 is our first term. Then we have a plus 1 over 2 minus 1 over 3. We have a plus 1 over 3 minus 1 over 4, so on, up to 1 over n minus 1 over n plus 1. So as you can see, a lot of these terms cancel out. This minus 1/2 and a plus 1/2 cancel out. This minus 1/3 and a plus 1/3 cancel out, and so on. We'll get all of these terms to cancel except this 1 and this minus 1 over n plus 1. We get this is equal to 1 minus 1 over n plus 1, which is equal to n over n plus 1. So now we have this example. We want to evaluate this sum. So this problem is a little trickier, but we're still motivated by the fact that we want to write this term as a difference of two terms. So first, we start out by rewriting this summand. So we have k factorial times k squared plus 1. So first we'll write this as k times k factorial. So this is this term right here, plus a k factorial. And that gives us k times k plus 1 factorial minus k factorial. So because k plus 1 factorial minus k factorial gives us this right here, and then plus k factorial. Then we can look at this term, this k times k plus 1 factorial, and then combine the other terms. So we have a minus k times k factorial plus k factorial, and this gives us k times k plus 1 factorial minus k factorial times k minus 1. And recall that k factorial is just 1 times 2 times 3 all the way up to k. So let's define f of n as n times n plus 1 factorial. Then we have f of n minus 1, just plugging n minus 1 in, is n minus 1 times n factorial. So then we can see that this term right here is f of k minus f of k minus 1. So this summation becomes f of k minus f of k minus 1. So we can expand this summation to get f of 1 minus f of 0 plus f of 2 minus f of 1 all the way up to f of n minus 1 minus f of n minus 2 plus, when k is equal to n, f of n minus f of n minus 1. So again, we see that a lot of these terms cancel out. We have basically everything canceling out except f of n and f of 0. So we've simplified this sum to be f of n minus f of 0. And going back to our definition of f, which we defined by looking at our simplified version of this, we get this is equal to n times n plus 1 factorial minus 0 times 0 plus 1 factorial, and this is just 0. So hence we get factorial. So that's our answer. Now you guys can try this checkpoint. So we have this definition of f of n, and you want to find this infinite sum. I'll just go ahead and go over the solution for this one since we're running low on time. So the first thing we can do is just write out a few terms of this summation. So we start with f of 2. So that's 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, so on. Just like plugging in 2 into this equation. Then our next term would be f of 3, is 1 over 2 cubed plus 1 over 4 cubed, 1 over 5 cubed. And then I'll just write out or f of 4. So we just have an exponent of 4 in the denominator. And so we want to sum all of these. So these rows look difficult to sum, but if we look at these columns, these are just geometric sequences. So basically, if we look at the kth column, let's just call this the second column for ease of notation. So for k is equal to 2, we want to find 1 over k squared plus 1 over k cubed, 1 over k to the 4th, so on. This is just a geometric sequence with first term 1 over k squared, and so we have a1 is 1 over k squared, and our common ratio is 1 over k. So the sum of this geometric sequence is a1 over 1 minus r. So this is equal to, this right here is k minus 1 over k. We get 1 over k squared times k over k minus 1. And this gives us 1 over k times k minus 1. So basically, we have this column sums to 1 over 2 times 2 minus 1. The next column sums to 1 over 3 times 3 minus 1. Sums to 1 over 4 times 4 minus 1, so on to infinity. And as we saw in the first example for telescoping, that 1 over k times k minus 1 be written as 1 over k minus 1 minus 1 over k. So this is equal to 1 over 1 minus 1 over 2. So that's this term. This term is 1 over 2 minus 1 over 3. This term is 1 over 3 minus 1 over 4, so on. And again, we see lots of cancellation. And since this is infinite, our last term is 1 over infinity, which is just 0. But this is just 1. So we get that our sum is 1. So that ends the lecture for today. We'll be moving on to Kahoot now.
Okay, so before we start the Kahoot, I think we'll take a short 5-minute break. So we'll start the Kahoot at 3:06. Okay, we're gonna start the Kahoot soon, so make sure to join. Still 5. Is everyone able to see
I say I'm too late. Got nothing in my brain. That's what people say. That's what people say.
Okay, I think we're just gonna start. You guys can still join if you haven't. If you're not in the game now. The game code is in the chat. Yeah, I think we should talk about this one. So the first term is going to be 5, right? And then the next one is -8, and then 13, No, not 3. 11, I mean. And then negative 14 and so on. So see, each consecutive pair is going to sum to negative 3. Oh. It's 3 times 1 plus 2, right? Equals 5. Okay, since there are 100 terms, that means that there will be 50 pairs of negative 3. So the answer is negative 150. Okay. Nice. Everything cancels, right? So you get 1 over 2007. Can we do it as number 1? Okay. Yeah, make sure that we want the 8th term, so that means we multiply 1/3 by 7 and add it to 2/3. Okay, so the sequence is 1, x squared, 9. And since x is in the middle, it'll be the average of 1 and 9, which is 5. So the answer is root 5. nice. All right, so you use the formula for the sum of 1 plus 2 plus 3 all the way to n, and you can solve for n then. Can we do it? It's still number 1. Okay, nice. All right, so you give the first friend 1 marble, and then 2 marbles to the next one, 3, and so on. And then that's 55 in total, so the answer is 21. Okay, so we can use the infinite geometric sequence formula here. A over 1 minus r equals 45. And then, since the common ratio is -1/2, we can plug that in. So that's a over 3/2 equals 45. And that gives us the answer of 135 over 2. Oops. Okay, for this one you can use sum of the geometric series formula. Since the common ratio is negative 2, you can plug it in and get it. Okay, nice. This is similar to the other one that we did actually, where everything else cancels out besides the 100. Okay, good. Reisen Yu Inaba takes the lead. Can we do it? Takes the lead again. Last question, by the way. Don't think too hard about this one. All right, so in order for the sequence to have strictly decreasing terms, m over 7 has to be less than 1, which is the common ratio. So m can either be from 1 to 6. So there are 6 possible values. Congratulations to anyone that participated. 46% correct.